Today, let us look at a concept called proof by contradiction. This is a technique that uses the fundamental theorem of arithmetic, which says that a composite number can be represented as a product of primes. Let us also look at another result. If p, a prime number, divides a square, then that implies that p divides a. Logically, that makes sense. But let us look at a few numbers and observe. If 2 divides 4, then 2 divides 2. 2 square is equal to 4. We see that 2 divides both 2 as well as 4. Let us look at 9 square. If 3 divides the square of 9, that is 81, then that implies that 3 divides 9. That also seems correct. Let us look at 25 square. Now, if 5 divides 625, that is the square of 25, then 5 would also divide 25. All these statements make sense. So let us take a composite number a and write it as a product of primes, p1 times p2 times p3 and so on times pn. Now if we square both the sides, then we see that a square is being expressed as all those factors squared. So all the prime factors are getting squared here. So if a prime factor divides a, then that prime factor divides a square as well. The corollary is also true, that if p divides a square, then obviously p divides a. Now we are going to utilize the fundamental theorem of arithmetic and this result, that if p divides a square, then p would divide a, and use them to prove certain problem statements. Exactly what kinds of problem statements? So a problem could be to prove that an irrational number is irrational. And the way we would solve this is to assume the contrary. That is, we would assume that the given irrational number is rational and then disprove it. Sounds confusing, doesn't it? Let us look at an example and follow the steps. So let us take an irrational number, for example square root of 2. Now we know that square root of 2 is irrational. But in order to prove that, let us assume that square root of 2 is rational. Now this is a contrary statement. Now if square root of 2 was rational, then we could express it as a upon b, where a and b are co-prime, which means that a and b have a common factor 1. They do not have any other common factor. In other words, we are saying that the fraction a upon b is in its simplest form. Why do we need to say that a and b are co-prime? Why is this important? Well, this is what we are going to contradict. And square root of 2 is irrational is what we are going to prove. So let us take the statement to prove in yellow and the statement to contradict in pink. Now let us get rid of the square root term. So let us square both sides and rearrange. We see that 2b square is equal to a square. Now this means that 2 divides a square. This also means that 2 would divide a. Recall that if a prime factor divides the square of a number, then the prime factor would divide the number as well. Now recall that the statement we are trying to contradict is that a and b are co-prime. So basically we are trying to prove that a and b have another factor in common. Since 2 divides a, let us assume another number c. So let us take a is equal to 2c and substitute this value of a in the earlier statement. 2b square is equal to a square. Simplifying, we get b square is equal to 2c square. Now this means that 2 divides b square. And this also means that 2 divides b. Now look at these two statements. 2 divides a and 2 divides b. But 2 is a common factor other than 1, which means that a and b are not co-prime. So we are contradicting step 2. Which simply means that our assumption in step 1 is wrong. We assumed that square root of 2 was rational. If that is wrong, then that means that square root of 2 is irrational. Now let us look at a few problems to get the hang of this technique. Prove that square root of 7 is irrational. So let us first make a contrary statement. Let us say that square root of 7 is rational. So we could write square root of 7 as a upon b, where a and b are co-prime. Let us follow our yellow and pink bubbles once again. Now first of all, let us square both the sides to get rid of the square root term. We see that 7b square is equal to a square, which means that 7 is a factor of a square. This also means that 7 is a factor of a. Let us call this statement 1. Let us assume a is equal to 7c and put this value of a in 7b square is equal to a square. Simplifying, we see that b square is equal to 7c square. This means that 7 is a factor of b square, which goes on to mean that 7 is a factor of b itself. Let us call this statement 2. Now from statement 1 and 2, we see that 7 is a factor common to a and b, which means that a and b are not co-prime. They have another factor in common. This is a contradiction. We said that a and b would be co-prime, whereas we have just proven that a and b are not co-prime, which means that our assumption that square root of 7 is rational is incorrect. So our statement in the yellow bubble is incorrect, which means that square root of 7 has to be irrational, and we have proven our problem statement. Let us look at another problem. Prove that 3 upon square root of 2 is irrational. So first of all, let us say that 3 upon square root of 2 is rational. So we could express it as a upon b, where a and b are co-prime. This time, the statement we are going to contradict is different. Let us rearrange our equation and write it as 3b upon a is equal to square root of 2. Note that now we have the irrational number square root of 2 on one side. So this is the statement that we shall contradict. Let us see how. On the left hand side, we see that 3b and a are integers, which means that 3b by a is rational. And what about the right hand side? What about square root of 2? We could simply state that square root of 2 is irrational. Or we could prove that square root of 2 is irrational and follow the first problem. So let us say square root of 2 is rational. Express it as a rational number p upon q, where p and q are co-prime. Square both the sides and say that 2 is a factor of p square, which means that 2 is a factor of p, and take p as 2r. Putting this value, we see that 2 is a factor of q square, or 2 is a factor of q. And we have just proven that p and q are not co-prime. Hence, square root of 2 is not rational. So we know that square root of 2 is irrational. Hence, the left hand side, which is rational, cannot be equal to the right hand side, which is irrational. And we have our contradiction. So our assumption is incorrect. Our assumption is in the yellow bubble, which was saying that 3 by square root of 2 is rational. Now since this is incorrect, we have just proven that 3 upon square root of 2 is irrational. You could also point out that if we knew that square root of 2 is irrational, then isn't it logical that 3 upon square root of 2 would be irrational? Well, that makes sense, but we have to prove it mathematically, and hence are proved by contradiction. Plus, we do not know whether division by an irrational number results in an irrational number itself. Let us look at another problem. Prove that 2 plus 5 times square root of 3 is irrational? First of all, let us say that 2 plus 5 times square root of 3 is rational and express it as a upon b, where a and b are co-prime. Now let us rearrange our equation so that square root of 3, which we know to be irrational, is on one side. Now this is the statement we shall contradict. On the right hand side, we see that a, b, 2 and 5 are all integers. Hence the right hand side, a minus 2b upon 5b is rational. And what about square root of 3? Here let us simply state that square root of 3 is irrational. You could follow the same method of proof by contradiction, just as we did in the last problem. Now since the left hand side is irrational, it cannot be equal to the right hand side, which we know to be rational. And here is our contradiction. So our assumption is incorrect. Hence 2 plus 5 times square root of 3 is irrational.